Any questions before we get started? All right, well, Chapter 9 deals with the chemistry of alkynes. Alkynes, we have a carbon-carbon triple bond. And it also serves as the intro point to the concept of organic synthesis. So we're going to do some chemistry of alkynes. As we do it, what I'm hoping is that you're going to look at this stuff and you're going to say, oh, I already know that. That's simple. I can figure that out. You're really to the point where this stuff should just really look familiar to you. So that's what we're shooting for. And then when we hit the part on synthesis, the questions that are here are basically presented in the format that I tend to use for synthesis on an exam. So this is an intro to what exam synthesis questions might also look like. Well, let's go ahead and get started. Way back in chapters 1 and 2, we talked about alkanes. Alkanes, we said, are composed of 4 sigma bonds. Those are the 4 sigma bonds. They're tetrahedral. It's sp3 hybridization. That means we take 1 s, 3 p orbitals, and we make 4 sigma bonds. Chapter 8, I think, we did alkenes and alkene reactions. We said alkenes are sp² hybridization, so our sigma network are the real covalent bonds, consists of 3 bonds, 3 orbitals, 3 bonds, so that's 1, 2, and 1 of those. The other bond in a double bond we said was a pi bond, because we have 2 p orbitals left over, and they make the pi cloud, which we show as a second bond. Today we're going to talk about alkynes. Alkynes are sp hybridization. That's 2 orbitals, 2 sigma bonds, and we're left with 2 pi bonds. The way all these go together is something like this. We start off with 1 s and 1 p orbital. Now remember, orbitals simply describe a region in space where you can expect to find electrons. S orbital, spherical. This is, p's are consisting of lobes on x, y, z axes. If we combine these 2 orbitals, and then we solve for the regions of space where we have minimum impact between electron clouds, we wind up with linear geometry. 2 orbitals, 2 sigma bonds, this one and 1 of these. Okay? And that's on each carbon. Now, each carbon also has 2 p orbitals left over. We haven't used yet. I'm calling these the py and the pz. So if we show these guys on these carbons, they kind of look like this. Those are our leftover orbitals. Now, when orbitals are aligned properly, they can overlap. When they overlap, when these guys overlap, they form molecular orbitals that look something like this. We have 2 molecular orbitals constructed of p orbitals, so we call these pi orbitals or pi bonds. We have 1 from these 2 guys and 1 vertical from these guys. These pi orbitals are what we refer to as the 2 extra bonds in our alkyne. All right, so that's bonding in just a very quick nutshell. The electron cloud surrounding an alkyne doesn't actually look so much like the pi orbitals. This is an electrostatic potential map. You can see right here between the 2 carbons, we have this huge belt of electron density. That's where the electrons are. This is where all the chemistry is going to happen. This end and this end are fairly positive. The fact that this is positive, kind of like the hydrogen of an acid, means that this hydrogen on the end of an alkyne is actually acidic. Now, it's not acidic in the terms of acetic acid or HCl or anything like that. It has a very high pK. pKa is about 19 or 20, but still, you can pull it off and make an anion. You can pull it off because it's blue here. Any question on the concept? All right, the first thing we always have to do with a functional group is name the compounds. We've done the rules for everything we've been through so far. We're going to look for a longest chain that contains the alkyne. The suffix we're going to use is YNE. We want to give the alkyne the lowest possible number. So those are rules that were, pretty much for everything that we've dealt with so far. So if we look at this guy, step one, we want to find our longest chain. It's going to look something like this. It's going to include the 2 alkyne carbons, and then 1, 2, 3 others. So we're dealing with a 5-carbon parent. Now, because it's a 5-carbon parent, it's going to be a pent. We want to give the alkyne the lowest possible number, so this is going to be carbon number 1. So our 5-carbon parent is going to have an alkyne at carbon 1, and it's going to have an ethyl group here at carbon 3. Putting them all together, we would write 3-ethyl, 1-pentyne. YNE tells you it's an alkyne. The 1 tells you it's at carbon 1, and of course we have an ethyl group at carbon 3. Yes?
We don't need to list the 1, do we? Is that optional?
Oh, no. No, we could have the alkyne in here at carbon 2, or not 2. Maybe on this, there is no other place to put it, but you have to put the number.
So it's not like ene, where we can just assume that for a carbon chain it's at 1?
No, no.
Okay, it's different.
The only time you can leave the number out for an alkene legally is if you're dealing with an alkene in a ring.
Okay.
Because in a cycloalkene, that is always defined as carbons 1 and 2. All right, let's look at this guy. We have a 4th rule. A lot of naturally occurring compounds, you'll see, contain both double and triple bonds. So we need to come up with a rule to handle those. The alkyne is actually going to be the parent, but the numbering is going to depend upon where the double bond is. So what you do is you look at the molecule and you say, if we started numbering here, would we get a different sequence than if we started numbering here? Just number sequence. No, we wouldn't. We're going to have a functional group here at carbon 1, regardless which way we start numbering. So the rule has to be a rule, and the rule is that the alkene wins. The alkene will get the lowest number. So, this is how we're going to number the thing. All right, now we have 2 functional groups in here that we have to include in our name. If we didn't have the triple bond, we would just look and say, okay, we have 8 carbons, and there's an alkene in carbon number 1. So we would call this simply a 1-octene. But at carbon 7, we have a triple bond, don't we? What the rule is to drop the E on the end. I'm not sure why, but they dropped the E on the end. Then they're going to put in the alkyne and its number. Now you don't have to call it an octine. All you have to do is put in the number and indicate that it's a triple bond. So we drop the E, and we have to indicate that in carbon 7, we have an alkyne. 1-octene 7-ine. Now in reality, in first semester organic on exams, we don't do a whole lot of numbering with multiple functional groups. All right, but if we do have multiple groups, this basically is going to show up a lot from now on, especially, where we have something describing the parent, and then we have something like this describing the second functional group. So you'll see this a lot with alcohols when we do chapter 17. Let's do one more here. Here we also have an 8-carbon parent. If we start numbering here, we will have our alkyne in carbon 1. If we started numbering here, our first functional group would be here at carbon 2. So here, the numbering sequence does make a difference. So we're going to let this guy be carbon 1. Now, in our octine, or octene, remember the ine is actually going to be the parent, the most important. We have a double bond, that's an alkene, at carbon 6. If you look at this, this has stereochemistry, doesn't it? Is this E or Z? Well, is it cis or trans?
Where do you see stereochemistry?
Right here. This is a trans double bond, isn't it? I guess I answered my question. What is trans? Trans is E. So, at carbon 6, we have an E alkene, E stereochemistry. At carbon 1, we have our alkyne. So, we're going to call this an E6-octene, again leaving out our last E. And in carbon 1, we have the alkyne. At this point, I would not really ask you to name this guy, but I would not feel real guilty about doing the reverse and giving you the name and either asking you to draw the structure or to pick the structure out from a collection. Yeah?
So if you had, at 6, if you had an apple coming out of there, that would make it a,
Up here?
that would, yeah, if you had that would make it a Z?
No, because this would still be higher priority.
So that's how you, okay. And then what I'm seeing is obviously the alkene, and alkene, that if it's not at the first, that doesn't matter. You're just looking at whoever has the bonds that are double or triple, whichever one's at the first. But if they're a tie, where they're at each end, you always go with the lesser amount?
Right. With the alkene, if it's a tie, rule 4 says the alkene gets the number.
Okay.
But otherwise, first of all, the alkyne is always going to be the main functional group. It is higher priority, so it's first. But the numbering depends upon the lowest sequence, giving the alkene the lowest number if it's a tie. All right, so test question. Name this guy.
It's where you just sacrifice the points and hope you did well on the rest.
Well, it's 18 carbons. Anyone know what an 18 carbon parent is? I don't either.
Like
It's a lot. It's a lot. Imine, whatever. And it's a alcohol. It's a diol. Probably it's best just referred to as onanthotoxin. Onanthotoxin is one of the toxic components of hemlock. If you recall, they executed Socrates by holding his mouth open and pouring hemlock extract in. Not a nice tea. Whatever. Anyway, this is just an example of a natural product that is a polyene diol. Lots and lots of stuff like that. Don't play with this stuff. Very toxic. All right. We are going to look at reactions of alkynes now. What you're supposed to do is initially be shocked and say, oh my goodness, here we go again. But I want you to look at all of these things and then think back to last week or so and say, well, wait a minute. We already talked about the addition of HX, of halogen, of hydration, of high deboration oxidation. We already did all those things with alkenes. So frankly, we already know all that, don't we? And it's going to turn out that all of these reactions are going to be very, very similar in concept to what we've done with alkenes. So this is one of those great moments in life where you learn something once and you get to use it over and over again. So that's supposed to make you feel good. If we have HX and an alkyne, all we're going to do is add it twice. And we're going to have Markovnikov regiochemistry. If we have halogen, so chlorine, bromine, iodine, we're just going to add it twice. If we do hydration, we're going to hydrate and make what's called an enol. It's going to look just like simple Markovnikov addition. However, the enol we'll see is going to isomerize into a carbonyl. That's kind of cute. High deboration. We know that this gives anti-Markovnikov regiochemistry. So we're going to make our alcohol, which rearranges to a carbonyl, just on the anti-Markovnikov carbon. Reduction. Simple. We did reduction with alkenes. We just make alkanes out of them. There are two unique reactions of alkynes for reduction. They're both partial reduction. One we'll see is going to give us cis addition. The other one will give us a trans addition. Finally, we talked about this way back in chapter 6. We're going to use alkynes as nucleophiles. That is, remember I said that this hydrogen was acidic. Because it's acidic, we can yank it off with a very strong base and then use it as a nucleophile in an SN2 reaction. All right, let's talk about that one first, because we've already done it back in chapter 6. And it's kind of a unique reaction among the alkynes. What we're doing is taking our alkyne. It must have a hydrogen on the end. So that's called a terminal alkyne. Has a hydrogen on the end. Do you need a... This is sodium amide. Sodium amide you actually make by taking a little vial of liquid ammonia and little bits of sodium metal, and you drop them in. You have to do it slowly because liquid ammonia, not nice stuff to play with, boils at very, very low temperature. The reaction with sodium evolves heat. So you do this, and as it dissolves, it makes the sodium salt. So this is actually NH2 minus. Very strong base, pKa of about 25 or so. So it's a very strong base. What this strong base does is simply pull off this acidic hydrogen, and you make the anion. Now, in this reaction, all you're going to do is take this anion and use it as a nucleophile. Once again, we talked about this in Chapter 6. All in the world that happens is that the anion attacks the carbon, the leaving group leaves, and we have made our new compound. This works really well if you have a primary alkyl halide. Works great with methyl, but it works really well if this is a primary carbon. Remember, that means it has a CH2 on it, and then something else attached. Primary carbon, SN2 reaction. The nice thing here is that in terms of synthesis, it allows us to take and build big molecules, starting with little guys. So here we've added just one carbon to our chain. Again, we could have added a lot. The same chemistry.
So
Any
how-
question?
that
Simple
would be-
SN2 reaction.
So how would that continue with the hydrogen at the end of it? It will continue growing and growing?
No, no, no. No, this stops right here.
Right.
But this could be anything. This doesn't have to be a methyl group. This
So-
could be a benzyl group, if you will. So we would introduce a CH2 and a benzene ring.
So it's important to remember the terminals, the hydrogens.
Yep, it's got to be a
Okay.
terminal alkyne,
Okay.
because that's the one that you can pull the hydrogen off to make the anion. All right, what we're going to do is just quickly run through the addition reactions now. And once again, the impression I want you to come away with is this is just like we did with alkenes. Our first one is the addition of HCl. HCl, HBr, HI. If you look at our starting material here, and you think about it in terms of Markovnikov addition, which one of these carbons on the alkyne would give the most stable carbocation?
Left?
Well, the secondary one, obviously. The secondary one is the most stable carbocation. You remember that. Primary carbocations would be less stable. So therefore, when we add HCl, it's simply going to add to this carbon, just like it did with alkenes. What we do is we form this intermediate, called a vinyl halide. Trivial name for the double bond is vinyl. So this is a vinyl halide. Now you look at it and you say the same thing. Which of these two carbons would form the most stable carbocation? What's an alkene? You already know that answer. This guy, of course, is not only secondary, but it's adjacent to a chlorine. Remember, anything with electron pairs can stabilize the carbocation. Therefore, our second mole of HCl is going to add to this carbon, and this is our final product. So in terms of just remembering things, this is Markovnikov addition. Step one, which carbon will give the most stable carbocation? You add 2 moles of chlorine to that carbon. That's bottom line. Any questions? We added halogens to alkenes. We remember from last week that we form a 1,2 dihalide. Well, here we have 2 high bonds, so all we're going to do is add 2 moles of halogen to it. So instead of a 1,2, we'll get what's called a 1,1,2,2 tetrahalide. Once again, it's stepwise. We add 1 mole here, and we make this. Just like with the alkene addition, the intermediate is trans geometry. Now this is just chapter 8 again. We have an alkene, we have bromine, just going to add again, and we wind up with the tetrabromide intermediate. Exactly the same logic. Any questions?
Yeah.
Okay.
How come on the bottom part of the problem you're showing, even though we're supposed to be adding it twice, that there's 2 BRs? I think I must have missed something.
Well, we add the first mole. Remember, we have 2 pi systems, 2 pi clouds, right?
Right.
So we're going to add the first mole to 1 pi cloud.
Okay.
Just like with alkenes, that addition goes trans.
So that bottom section that you're showing for this problem and the previous one is showing what the first
What the
mole of
intermediate
BR2.
is, right?
Okay.
The first mole goes here, the second mole goes up to here.
Right, so the intermediate is trans. Okay, thanks.
All right, let's say we had an alkene and we did hydration. Here we're going to add water to our double bond and we get an alcohol. We're going to do the same thing here. We have a triple bond and we have water. Now remember, we had 2 ways to add to a double bond. One was just water and acid. That was not civilized at all. The more civilized way, we threw in mercury ion. Mercury ion catalyzed the reaction. Well, with alkynes, it doesn't work well unless you have the mercury present. So we don't just do acid and water. Here we need to do acid and mercury. We look at our starting material again, and you ask, which of these is the Markovnikov carbon? Okay, which is the Markovnikov carbon? That is, which of these would form the most stable carbocation? We have a secondary and a primary. Well, we already know that answer, don't we? The secondary is going to be the most stable carbocation. So therefore, if this was an alkene, you would simply add the hydroxyl group to this carbon. We'd wind up with this as our product. The thing that's unusual here, this guy is called an enol. Now the name comes from the fact that we have an alkene, that's the ene, and we have an alcohol, that's the ol. It's an enol. Next semester, unfortunately I won't be teaching this next semester, but next semester you will have a great deal of exposure to reactions involving enol intermediates. It's going to be a very important part of 235. But the neat thing about an enol is that it can undergo a rearrangement. It's actually called a tautomerization. Tautomerization, you simply move a hydrogen from one end of the molecule to the other. The rearrangement occurs, the carbon-oxygen turns into a double bond. This end turns into a CH3. Now, this looks a little bit like magic. It's not. Let's look at it a little more closely. Here's our enol. On this carbon, it's an sp squared carbon, isn't it? We have an oxygen sticking out. This is an sp squared carbon also. What we're going to do is simply move this hydrogen from up here to down here. So it's a tautomerization. An isomerization that simply, it's a rearrangement that simply involves moving a hydrogen.
How do you spell that?
Tautomerization is a T word. All right, the way this magic happens, a base is going to come. It's going to pull this hydrogen off. When it does, these electrons are going to move in to form the carbonyl. These electrons are then kicked out, and they pick up a hydrogen on this carbon. The oxygen becomes a carbonyl. This end of the alkene, in this case, picks up the hydrogen and becomes a CH3. Enol ketone.
Sorry, again. Is the reason it never goes to the benzyl ring, that double bond, is because of Markovnikov's original chemistry? Like,
You mean in the original addition?
in this movement, like the base. Like
Well, there's no
H is
place
gone.
to put those electrons. Remember, we can only do this through a pi system. The electrons flow from here out to here, where they pick up the hydrogen. If you think about it, if we didn't have this hydrogen here, we would have a negative charge right here, wouldn't we, on that carbon?
Right.
The thing that you will do at 235 is just like we use the alkyne anion as a nucleophile. In 235, you'll use that carbanion as a nucleophile. Kind of a neat reaction, called an aldol type ionization. Something to look forward to. Any questions? All right, well, let's kind of do this over again, just slightly differently. When we talked about alkenes, we had two ways to make alcohols out of them. One was Markovnikov, and the other was anti-Markovnikov, right? The anti-Markovnikov used BH3 and a solvent like THF, followed by peroxide. That was the anti-Markovnikov alcohol. So we're going to do exactly the same process. We're going to look at our triple bond, and we're going to say which is the Markovnikov carbon. That's the carbon that would give the most stable carbocation. Our choices: primary or secondary. Markovnikov carbon would be the secondary one, wouldn't it? Now, this is an anti-Markovnikov addition. Therefore, the hydroxyl group is going to go here. This is the enol that we make in this case. Now, very quickly, we know that this enol is going to undergo rearrangement to give a carbonyl. On your little piece of paper, make sure you can draw the carbonyl compound. It's going to show up on the slide in about 10 seconds. Carbon skeleton is going to be the same. Where the oxygen is, this is going to be a double bond, going to be a carbonyl. And the other end of the alkene is going to have the hydrogen. What we've made is an aldehyde. Why is this an aldehyde and the other one was a ketone? Well, because what's attached here? Hydrogen and our enol hydroxyl group. So, hydrogen stays in the same place. This becomes a carbonyl. This becomes a CH2. Any questions?
So there's always going to be whenever you see a B, in other words, or not B, but VH3, that's always anti-Markovnikov.
Always anti-Markov. When you see BH3, THF, and oxidative workup, that should scream at you, anti-Markovnikov. Okay? Organic chemistry screams at you. All right, with alkenes, we did reduction. We're going to do exactly the same thing with an alkyne. Remember, we have two pi systems here. So we're going to add 2 moles of hydrogen. Once again, our catalyst is something like platinum or palladium, usually on charcoal, just to help spread it out. All we've done here is convert a triple bond into a single bond. We've added 2 moles of hydrogen. Now, this reaction yields an alkane, right? Alkanes are probably the most boring functional group because you can't really do much with them. There are other ways that you can reduce only one of the pi systems here. That means we'd wind up with an alkene. And that's more useful because you can do more chemistry on the double bond.
What mole of hydrogen with that?
No, if you had 1 mole of hydrogen, this would only go 50%. What you have to do to make this work is to use a really rotten catalyst. This is called Lindlar catalyst. It's also referred to generically as a poison catalyst. What this is just a really rotten catalyst. Instead of taking our platinum or palladium and putting it on charcoal, which is inert, basically you put it on something like barium sulfate. The sulfate reduces the effectiveness of the catalyst so much, it's such a lousy catalyst, that it's strong enough to add to one pi system, but not the other. Now remember when we talked about reduction of an alkene, we said that the addition was cis, right? That the stuff sat down on the surface, both hydrogens came on at the same time from the same side. Therefore, Lindlar catalyst gives us a cis alkene. Why is this useful synthetically? Again, because we can take this and we can do all those reactions we know to it. There's another way that we can reduce. It's a little more exciting. This one uses liquid ammonia. What you do is you take your alkyne and you dissolve it in liquid ammonia. Then you take little bits of lithium metal and you drop it in slowly. Again, the reaction involves heat, so you have to do it very slowly because you don't want it to blow up on you. The neat thing here is that this is a radical reaction. Now we'll talk about radicals again next time. But in a radical reaction, we're going to add hydrogen atoms one at a time. Because we add them one at a time, the intermediate here has enough time to get to the most stable conformation. Remember, cis is less stable than trans, because in a cis, the alkyl groups bump into each other, and the trans are as far apart as they can get. Therefore, the dissolving metal reduction gives us a trans alkene. Lindlar catalyst gives us a cis alkene. A regular catalyst gives us an alkane. Dissolving metal, that's lithium, liquid ammonia, gives us the trans alkene. Any questions? All right. If we took an alkene and we treated it with acidic potassium permanganate, what would we get? What would you get? Well, we know that acidic permanganate will split the alkene, won't it? Same thing is going to happen with an alkyne. If we take our alkyne and we have acidic potassium permanganate, what we're going to do is simply split our carbon-carbon triple bond, and we're going to wind up with 2 carboxylic acids. Now, your job here, look at this. Convert each of these carbons into a carboxylic acid and draw the structure. For this side, nothing's going to happen to the benzene ring. It's just going to sit there. This is the carbon. This is going to be a carboxylic acid. Remember, a carboxylic acid is COOH. So from this half of the ring, this is the structure we will get. Benzoic acid. We all know and love benzoic acid. We even used it in lab. The other carbon of our alkyne. Going to split this off here. Nothing's going to happen to the methyl group. This carbon will be a carboxylic acid, making this acetic acid. Acetic acid, the acidic component of vinegar. Any questions? All right, well, the good news is that's really all the reactions that we have to worry about. We're going to do Markovnikov additions. We know how to do those. We're going to add halogen. We know how to do that. We're going to do reduction. Turns out that there are 3 ways to do it. We can use a strong catalyst and reduce everything. Use a poison catalyst and get a cis alkene or dissolving metal and get a trans alkene. Again, oxidation gives us carboxylic acids. exactly what you learned last week for alkenes. So let's do some reactions. Very quickly, take these guys and draw the structure of these products. Mary Jo, we left this last week. All right, our first one. This is going to be addition of HCl. What do we know about that? It's going to be Markovnikov addition, isn't it? So we look at our starting material and say, which of these is the Markovnikov carbon? Well, it's a tie. They're identical. So the first chlorine is going to go somewhere. The second chlorine will go to exactly the same spot. And we will add both and get this as our structure. Doesn't matter which one, they're identical. Our next one, we look at the conditions and we say, all right, hydroboration oxidation. I know that. That's anti-Markovnikov alcohol. I'm going to put an OH group on the anti-Markovnikov carbon. The secondary carbon here would give us the best carbocation. This is the anti-Markovnikov carbon, so the OH group ends up there. But we say to ourselves, that's going to give us an enol. So instead of an OH, we're going to have a carbonyl here. And this is simply going to be a CH2. So the structure we've all drawn looks like that. Our terminal carbon here, that's going to form our enol, so the oxygen goes there, then it rearranges to form the carbonyl. We have an alkyne. Our next reaction is dissolving metal reduction. Liquid ammonia, we're dribbling in lithium. We know that that would give us a trans-alkene. Frustratingly enough, however, this has a hydrogen on there. So the trans is going to look just like the cis, isn't it? So we're just going to wind up with a double bond here.
Like the way you're saying that right now is.
I'm sorry?
The way you're saying that is like someone, like the way you're talking to me at least. I can't get that like right now. Like the way you're talking to me. So
well,
all I'm looking at is clues here. One is the NH3, and then we have the terminal. Because I mean, unless.
Well, okay. All right. We look at our conditions. Lithium, liquid ammonia.
Causes a trans.
Right. That is reduction. Partial reduction. We would get a trans double bond.
Okay. And if there's a terminal,
but
watch out for that.
because this is a terminal alkene, we're going to put a hydrogen here. Cis and trans has no meaning, does it? So that's all that is. Yes, the addition of these hydrogens goes on trans, but you can't tell because this is a CH2. That's all that means. Any question on these three? All right, another one here. Once again, hydroboration oxidation. What does that give us?
Anti-Markovnikov.
Anti-Markovnikov, right. So we're going to make an alcohol. It's going to be enol. Now we look at our starting material. Which of these two would be the most stable carbocation? Don't make me say it.
The first one.
What is this guy?
That's Scott Ford.
That's a benzyl position, isn't it? One of our favorite carbocations. Therefore, this is the Markovnikov carbon, and the other guy is going to get the OH group. We know that that OH is going to convert into a carbonyl. So this carbon will be a carbonyl. This guy will be a CH2. The product that we've all drawn simply looks like that. The oxygen goes to the anti-Markovnikov carbon. Next, we're doing hydration. We know that this is going to be Markovnikov. So you simply look and say, which of these is going to be the more stable carbocation? That's where the oxygen goes. We have a secondary and a primary. Our most stable carbocation is clearly the secondary. So, in the enol, OH is attached here. That means that in the final product, this is going to be a carbonyl. This guy is going to be a CH3. And it looks like that. Oxygen is attached to the carbon in our starting material that would give the most stable carbocation. Now, the really neat thing about this problem is making you draw it. It's actually not so difficult to draw. It's a tricyclic compound. It's an adamantane derivative. This is the structure, the basic structure of a diamond cubic cell. Here we have sp3 carbons all the way around. In a diamond, they would just be carbons with no hydrogens. And this matrix continues out in all directions. That's why diamonds are so hard, so strong, because the geometry is perfect. All right, so this guy, treating it with sodium amide. What does that do? Well, it's going to pull off this hydrogen, isn't it, to make an anion. Once we have the anion, what happens? That's a nucleophile in an SN2 reaction. All we're going to do is lose the hydrogen and stick the methyl group on. Draw structure, and it should look like that. Adamantane itself is a very interesting compound. If you take adamantane, instead of this alkyne here, if you have just an amino group, an NH2 there, that was the very first antiviral drug to be developed. All right, one compound and three reactions. We are doing dissolving metal reduction. We are doing reduction with platinum on charcoal, or we're doing reduction with Lindlar catalyst. I will pause for a moment while you draw 3 compounds for your answer.
Is there a poison in there or no?
Yes, Lindlar is a poisoned catalyst. When you look at reactions, reactions need to, like I said, scream at you. There's only a few things you know about every reaction. When you see it, it should immediately come to you. When you see lithium and liquid ammonia, that should tell you we're doing reduction. We're going to stop at the alkene. And the stereochemistry will be trans. That's what you say to yourself. You're doing reduction, going to get an alkene, and it's going to be trans. The alkene should look like that. The next thing we're doing, hydrogen, platinum, and charcoal. That's a big time catalyst, isn't it? Because we have a big time catalyst, we're going to reduce both pi systems, and we're going to wind up with this diarene. We reduce this to simply an alkene. Then finally, hydrogen and a poisoned catalyst. We remember a poisoned catalyst just doesn't work very well. So it's only going to add to one of the pi systems. When it does that, we're going to add them from the same side, which means our stereochemistry is going to be cis. Now I'll give you a very blatant hint. This is a classic exam question. Okay? Make sure you know this. It's a classic exam question. Any questions on these? In our first reaction, what are we doing? We're adding halogen. If it was an alkene, we would say, okay, no problem. We're going to add halogen, going to form a trans dihalide. Here we have 2 pi systems, so we're going to form a tetrahalide. Every carbon hits a chlorine. This is cheating, going back to chapter 8. We didn't do HBr peroxide with an alkyne because it doesn't work. But we remember, when we see this reaction, what does it scream to you? It says, I'm going to add a bromine, and my regiochemistry is going to be anti-Markovnikov. So we look here and we say, which one of these is the anti-Markovnikov carbon? This is tertiary, that's secondary. Carbocation would be here. We're going to put the bromine here. And finally, we have an alkyne, and we have a poisoned catalyst. We know that's going to give us an alkene. Going to stop at the alkene because it's poison. And our stereochemistry is going to be cis. Any questions? All right, what we're going to do next is to take everything that you know and we're going to apply it to organic synthesis. We're going to start off this way. Here I have 4 different compounds. I'm going to let you start with, quote, any appropriate alkene. And make these guys, you can make them all in one step. We'll take a 10-minute break or so, and then we'll come back and we'll do organic synthesis.